Hello everyone, I am Honako, a PhD scholar at IIT Kanpur. Today I will discuss week 8 of Fundamental of Supersonic and Hypersonic Flow. In this week 8, mainly implicit high temperature equilibrium flow was studied, and mainly the topics of normal soak, oblique soak, flow in the nozzle for the chemically reacting gas mixture was studied, and what is the equilibrium flow, fusion flow. So we will solve some problems related to it. There was one expression which was shown in the slide, which was for equilibrium constant. For equilibrium constant, in terms of partition function. So equilibrium constant Kp is given by product of Pi to the power nu I, where nu I is stoichiometric coefficient of a reaction, equal to Kt upon V. V here is volume, K is Boltzmann constant, to the power sigma nu I e to power minus delta epsilon naught upon Kt. Delta epsilon naught is 0 point energy of products minus 0 point energy of reactants. And Pi is partial pressure of species I. And Qi is partition function for species I. So for this derivation, first let's see what is a generalized chemical reaction. It is known by nu1 dash A1 plus nu2 dash A2 plus so on nu k dash AK, and it will give nu dash k plus 1 AK plus 1, nu dash k plus 2 AK plus 2, and so on nu j dash AJ dash, where this A1, A2 to AK are reactants and AK plus 1 to AJ are products, and nu1 dash nu2 dash and so on to nu j dash are stoichiometric coefficient of their respective species. Now we will take all the reactions to right hand side. So we can write this chemical reaction as 0 equal to sigma I nu I AI, where this terms nu I dash has only the positive value, but the nu I can have positive or negative both values. So for the statistical thermodynamics, NJAI, this NJAI is number of atoms or molecules of AI in GH energy level, and it is equal to NAI. NAI is number of particles of species AI. Similarly, GJAI is degeneracy of AI in energy level J, and QAI is partition function for species AI. Derivation of this equation NJAI equal to NAI GJAI e to the power minus epsilon JAI upon KT upon QAI. It is similar to the for the single species gas, and this equation is for mixture. For mixture and chemical reacting flow, we will get one more equation, which is product of NAI to the power mu equal to e to the power minus delta epsilon naught upon KT into pi into product of QI to the power mu. Here this delta epsilon naught is nothing but the difference of 0 point energy of product and reactants. So now we will see from perfect gas relation PIV for each species I, PIV equal to NAI KT. NAI is number of particles of species AI. So we can write PI equal to KT upon V into NAI. If we raise it to the power of its stoichiometric coefficient, it will become PI to the power mu I equal to KT upon V to the power mu I into NAI to the power mu I. If we take its product, it will become pi I PI mu I equal to pi I KT upon V to the power mu I into NAI to the power mu I. It is product, so we can write both products separately also. So this for this term, this product will be this pi NAI to the power mu I, and for this term, if you see, if we take the product of KT by V of with having different powers, different exponents, so it will become summation. So it will become KT upon V to the power sigma mu I pi I NAI to the power mu I. Now we know that what is the value of NAI to the power mu I? It is nothing but E to the power minus delta epsilon naught upon KT into pi I QI to the power mu I. We will substitute that value here, so we will get it equal to KT upon V to the power sigma mu I into the power minus delta epsilon naught upon KT pi I QI to the power mu I. This is the relation for equilibrium constant. Here we have not derived how we got this relation. This relation also we have not derived, but it is similar to for single species gases. How these relations are derived, you can search in book Physical Gas Dynamics. By infinity. Now we will see other problem. This is choose the correct option in connection with the H2 upon H1 ratio across the normal shock. Statement 1, H2 upon H1 equal to function of M1 for calorically perfect gas. Statement 2, H2 upon H1 equal to function of U1, P1, T1 for equilibrium chemically reacting gas. Statement 3, H2 upon H1 equal to function of M1, P1 and T1 for equilibrium chemically reacting gas. So there are four options. Statement 1 false, statement 2 true, statement 3 false. So basically we have to tell which of the statement is true or false. You have to find it. For first we will see what are the governing equation for normal shock. So continuity, there are some assumptions for this normal shock, like flow is steady, it is adiabatic, and there is no body force involved. So if we take and the flow is invisible, if we take all these assumptions, we will get these equations. For continuity, we will get ρ1 u1 equal to ρ2 u2, momentum u1 equal to ρ1 u1 square equal to p2 plus ρ2 u2 square, energy we will get h plus u square upon 2 equal to constant, or it can also be written as h1 plus u1 square upon 2 equal to h2 plus ut square upon 2. So here I have written in the form of h but not CPT, because this is the general relation we can use for any type of gas, like calorically perfect gas, thermally perfect gas, or chemically reacting gas mixture. But if we write the CPT here, then it can only be used for calorically perfect gas, because then the Cp will be constant, or function of temperature also. So this Cp can be variable. So that's why we are not writing it as some CP. So this continuity equation, this U2 can be written as ρ1 upon ρ2 into U. Momentum equation also, we have this momentum equation, this term ρ2 U2 square. So it can be written as ρ2 U2 into U2. This ρ2 U2 from continuity we can write ρ1 U1. So it will become U2 plus ρ1 U1 U2. Now this U2 will substitute from this continuity equation. Then we'll get P1 plus ρ1 U1 square equal to P2 plus ρ1 U1, this ρ1 U1 into ρ1 upon ρ2 into U2. If someone joined, so I was talking about this one problem in which we have to tell which statement is true or false. So the problem was what is H2 upon H1 across a normal shock. So for calorically perfect gas, it is function of M1. Statement 2, for equilibrium chemically reacting gas, it is function of U1, P1 and T1. And for statement 3, for equilibrium chemically reacting gas, it is function of M1, P1 and T1. So I was telling about what are the governing equations for normal shock, and we got P2 equal to P1 plus ρ1 U1 square into 1 minus ρ1 upon ρ2. Only these are these three governing equations. I am writing only in different forms only. continuity ρ1 E1 equal to ρ2 U2, momentum E1 plus ρ1 E1 square equal to P2 plus ρ2 U2 square, and energy equation H1 plus E1 square upon 2 equal to H2 plus U2 square upon 2. So energy equation is this H1 plus E1 square upon 2 plus H2 plus U2 square upon 2. U2 square I substituted from this continuity here, so it will get H2 plus half ρ1 upon ρ2 whole square into U1 square. So we will get H2 equal to H1 plus U1 square. This term I will take on left hand side and take common U1 square upon 2. So I will get H1 plus U1 square upon 2, 1 minus ρ1 upon ρ2 whole square. So for finding H2, it depends on H1, U1 and ρ1 by ρ2. And H1 is nothing but function of pressure and temperature, E1 and T1. So it becomes function of P1, T1, U1 and ρ1 by ρ2. If you see from this pressure equation, if you know U1 and P1, then you will get this ρ1 by ρ2 also by using this all relations. So then basically this H2 is only a function of this H2 by H1 is function of only P1, T1 and U1. So for chemically reacting gas, this statement 2 will be true. Now there might be one question, if we can write it in terms of this U1 and T1, so we can also write this in terms of P1, T1 and M1 also. But the issue is that you might have studied frozen flow and clean flow. For finding the Mach number, we need U upon A, speed of sound, and this speed of sound is different for medium flow. We get two different speed of sound, one for medium flow and one for frozen flow. So there is a very big difference between those two Mach numbers. So different places can use different Mach number also. So not to create any confusion, generally it is used only velocity only for this type of flow. So this H2 upon H1 is not function of this Mach number E1 and T2. This is false. And for calorically perfect gas, there is already a derived equation for T2 by T1, and H is only function of H is given by Cp into T. The Cp is constant. So H2 by H1 is nothing but T2 by T1. And its relation can be derived, which is given by 1 plus 2 gamma upon gamma plus 1, m1 square minus 1 into 2 plus gamma minus 1, m1 square upon gamma plus 1, m1 square. And if you see, this relation is only function of m1. So this statement is also true that H2 by H1 is function of m1 only for calorically perfect gas. First and second statement is true and third is false. So it is in option C. Statement 1 and 2 are true, 3 is false. Is there more about why we are not using this Mach number? I will maybe tell later also. Now we will see the next problem. this problem is choose the correct option regarding temperature behind the normal shock. Calorically perfect gas results over predicts the temperature behind a normal shock. This is statement 1. If statement 2 is for calorically perfect gas, the dielectric kinetic energy of the flow after shock is converted mostly into translational and rotational molecular energy behind the shock. You have to tell which statement is true and which is false. So this is one plot of T2 by T1 versus velocity U1. So if you see this plot, this dash lines are for calorically perfect gas and the solid lines are for real gas at different pressure or density. If we see one velocity and check for real gas, the temperature we are getting is lower than, very low than what we are getting in calorically perfect gas. So we can see that the calorically perfect gas over predicts the temperature behind a normal shock. So this statement 1 is true. And now the reason for this, why it over predicts. So for what happens in chemically reacting gas, the kinetic energy, let's say this normal shock, across a normal shock, this kinetic energy is converted to thermal energy. So what happened there? This thermal energy, some of it is used in exciting the chemical reaction and vibrations. So vibrational mode and electronic mode can also be excited, and there can be dissociation and ionization of the gas, which requires the energy. So due to which some of energy is absorbed by other modes other than translational and rotational. And as we know already, then temperature is mainly given by this translational mode of energy. So as some of the energy is distributed to other modes of energy also, this temperature which we are getting for the equilibrium chemically reacting mixture is lower than calorically perfect gas. And in the calorically perfect gas, there is no chemical reaction happening. So there is no need for energy for dissociation or ionization of the gas. So mostly the energy will go for translational and rotational energy modes. So the temperature will be higher due to high translational energy. So the statement 2 says that for calorically perfect gas, directed kinetic energy of the flow I.4 is converted mostly to translation and rotation molecular energy behind the shock. This is also true. So both statements are true, which is only option D. So option D is the correct one. In this plot, there are effects of this pressure also. This I will discuss later. There is one more problem related to it also. Now we'll see the next problem. For equilibrium chemically reacting gas, the relative kinetic energy of the flow ahead of normal flow when converted behind the shock. So, before in this problem we already told that for calorically perfect gas it is mostly converted into translation and rotational energy. But what happens in this one? Uh, First we'll see the four option. There can be multiple also. So what happens in this one, that energy is conferred in the all modes of energy. So let's check the options also. Option A converts entirely into translational energy. This is wrong. In the calibratory perfect gas also it is shared with the rotational energy also. So it is wrong. And for the chemically reacting gas, it is shared with all energy modes, like in the option B, shared across all molecular energy modes, translational, rotational, vibrational, electronics if applicable. So this is true. You already told before. And option C goes into 0 point energy of the products of the chemical reactions. So what happens is, if there is dissociation of molecule, then you will get atoms, and the combined 0 point energy of atoms is greater than 0 point energy of molecule. Like if this is the 0 point energy of atoms combined. Combined after, let's say after dissociation of AB, we are getting A plus B. So the combined energy of this A and B will be greater than this AB. Let's say this is the energy, 0 point energy of molecule. So this delta will be positive. So sum of the energy, which is sum of the kinetic energy of the flow, will be goes into the 0 point energy of this atoms, or you can say products of the chemical reaction. So this third point is also correct. Option D, temperature is less for an equilibrium reacting gas than a calorically perfect gas for the same upstream condition ahead of the flow. In this figure we already saw there are same upstream condition for T1 equal to 25 Kelvin, and the temperature which we are getting for chemical reacting gas was very high compared to what we are getting for equilibrium chemical reacting gas. So it means that temperature is less for equilibrium chemical reacting gas than calorically perfect gas for the same upstream condition at the source. This is also true. So reason for this also, you can see that this B and C are reason of this only. That the kinetic energy of the flow, which is ahead of normal salt, will be shared for in the all molecular energy mode, and some will go in the 0 point energy of the product. So if we compare with the calorically reacting gas, let's say this is the amount of energy total. This is the total amount of energy, kinetic energy. If for the calorically reacting gas, it was let's say this half and half. Okay? Some half was going for translation, half was going for rotational. I am telling only assume it is not correct that half and half will go. This is for calorically perfect case. And same amount of energy, it will share the multiple things. Like translational, rotational, vibrational, electronic energy, or this zero for 0 point energy. So for translational, it is very less of energy compared to before. So this temperature, this is for chemically reacting gas. So it has less temperature. Now we will see the next problem. Choose the correct option in connection with pressure ratio across the normals of occurring in high temperature inviscid equilibrium flow. There are 4 options. Pressure ratio is not strongly affected in high temperature air. Option B. Pressure ratio is strongly affected by high temperature in inviscid chemically reacting air. Option C. Pressure behind the shock is approximately dependent on upstream velocity and density. Pressure ratio across the shock is dependent only on upstream Mach number. One thing is that we already told that for the high temperature inviscid equilibrium flow, we are not considering Mach number, only velocity. So this will not come. Option D. And from option B and C, you can see only one can be true, because one is telling not strongly affected, one is telling it should be strongly affected. So for this, there is one table which I have taken from high temperature gas dynamics, hypersonic and high temperature gas dynamics by Anderson. I have written table number also, so you can check later also. So it gives the properties occur for normal shock wave in air at velocity of 36,000 feet per second and an altitude of 1,70,000 feet. So these are the flow properties: T2 by P1, D2, O2 by ρ1, H2 by H1, T2 by T1. And it is given for calorically perfect gas and for equilibrium chemically reacting air, which is taken from CEL report and this report number. If you see that for pressure ratio, for calorically perfect gas it is 1233, and for chemically reacting gas it is 1387. There is not much difference. These are of the same order. So you can see that the pressure ratio is not strongly affected by high temperature. So this option A is correct and option B is wrong. You can see other properties also, like density. There is very big difference in density, approximately 3 times. Enthalpy is also not affected by it. And temperature is also very much difference. You can see with this number. The change in pressure is less because pressure is mechanically oriented variable. It is governed mainly by fluid mechanics of the flow and not so much by thermodynamics. Now we will see what this pressure behind the shock depends on. So this was the governing equation, momentum equation for normal shock, which we saw before. P1 plus ρ1 U1 square equal to P2 plus ρ2 U2 square. And for hypersonic flow, if we see this table also, just see how much this ratio is P2 by P1 or U2 is not given, but U2 by U1 is also very less. So this P2 by P1 is very high, so P2 will be very much greater than P1. And similarly, this U2 will be very less than U1. So we can ignore this P1 and U1 term. So P1 and U2 term. So we can ignore this P1 and U2 term. If we ignore it, then we will get P2 is approximately equal to rho 1 U1 square, which means it is function of rho 1 and U1. It means upstream density and velocity. So option C says this only, so it is also correct that pressure behind the shock is approximately dependent on upstream velocity and density. Now we will see the next problem. It is also a true and false problem only. Choose the correct option regarding the influence of pressure on moderation of T2 by T1 for normal shock formed in equilibrium high temperature air. So before we have seen the effect of gas, like what type of gas has for the T2 by T1 across a normal shock. Now we will see what is the effect of pressure. In equilibrium high temperature, statement 1. In equilibrium high temperature dissociated and ionizing air, an increase in pressure at fixed temperature would increase the dissociation and ionization of air. Statement 2. T2 by T1 increases as pressure is increased. For equilibrium high temperature dissociating and ionizing air. You tell which statement is true and which is false. So one thing is that in equilibrium dissociating and ionizing air, increase in pressure at constant temperature reduce dissociation and ionization rate. So it will not increase, it will reduce. So this statement 1 is false. This is false. So what will happen that if there is dissociation, if let's say pressure increases, what happens? Dissociation and ionization decreases. If this dissociation and ionization is decreasing, it means less energy is required in chemical reactions and vibrational mode. Vibrational mode of energy. So if less energy is required for vibrational and vibrational mode of energy in chemical reaction, what will happen? It will have high temperature. High temperature, or you can say it will have more energy will go to translational and rotational mode of energy. If there is more energy in the translational mode of energy, it means it will have higher temperature. So T2 by T1 increases as pressure is increased for equilibrium high temperature dissociating and ionizing air. This only we told, if P pressure is increased, then it will also have higher temperature. Temperature will also increase. So this statement 2 is true. So answer will be first statement is false and second is true. Option D. This is the same plot which I have shown before. It is about temperature ratio versus velocity. So about this chemically perfect gas, we already know that energy will go only in translational and rotational mode. So it will have high temperature compared to real gas, in which energy will go in all modes of energy. Now, what happens that when pressure, let's say for constant temperature P equal to rho RT, so if P increases, it means rho increases, or rho increases, it means P increases. So wait, in this plot, this unity atmosphere, but symbol is for density. So I think there is one typo. So either this is density. Wait, let me check in time. So this is for pressure, not density. There's one typo. So you don't need to see this. So if you see here also, this pressure is decreasing here. So as pressure is decreasing, it means decrease of pressure will increase ionization, dissociation. If ionization, dissociation is increasing, it means more energy is going to vibrational modes and for 0 point energy. So and chemical reactions also. So if it is happening, it means the energy in the transmission mode of energy is less. So the temperature will decrease as pressure decrease, or vice versa. Okay. Now we'll see the next problem. Choose the correct option in connection with oblique shock formed on a wedge for high temperature air. The maximum deflection angle theta, which allows a straight oblique shock, is increased for equilibrium high temperature chemical reacting air compared to chemically perfect gas assumption. Statement for first option is telling that let's say this is one wedge, and this is one shock. So this is deflection angle theta, shock angle eta. So as we increase this theta, we will reach one angle theta max, after which the shock will detach. So after this angle theta max, the shock will detach. So in this question, it is in this statement, it is telling that the maximum deflection angle theta is theta max, which allows a straight oblique shock, is increased for equilibrium high temperature chemical reacting gas compared to chemically perfect gas assumption. So it is telling that theta max for equilibrium chemically reacting gas is greater than theta max for calorically perfect gas. This is first statement. We don't know if it is true or not currently. Statement 2. Oblique shock for equilibrium high temperature chemical reacting air lies further away from the body compared to calorically perfect gas assumption. So in this question it is asking that if this is oblique shock, so let's say this is figure only, this oblique shock for equilibrium high temperature chemical reacting gas lies further away from the body compared to calorically perfect gas assumption. It means for it is telling that let's say this is the shock for chemical reacting air and this is the shock for calorically perfect gas. So this is away for chemical reacting gas, it is more away from the body. Now we'll check both of these. So this is figure is given for shock angle versus flow deflection theta. This deflection angle, wave angle, velocity diagram, this theta, beta, v diagram. In high temperature at 1 lakh feet altitude. This is also taken from Anderson only, hypersonic and high temperature gas dynamics. So here this dotted figure, these two dotted figure are for calorically perfect gas. These two dash figure are for calorically perfect gas. Rest of the figure are for chemical reacting gas. For the same also, you see that for V1 equal to 5000 feet per second, this gamma equal to 1.4, it means calorically perfect gas. And for this figure, for chemical reacting gas, you can see that this theta max is higher than this theta max. So you can see that this theta max for chemically reacting gas is greater than theta max for calorically perfect gas. And you can see this also that for Mach number, upstream Mach number tends to infinity, this theta max for this value is coming around let's say 45, 46, but there is also cater for different velocity. For chemically reacting gas, we are getting higher theta max also. One more thing, the oblique shock for equilibrium high temperature chemically reacting gas lies further away from the body compared to calorically perfect gas assumption. It is not clear in this one, so I will draw one more figure. This is beta, this is theta. If this is for calorically perfect gas, then this figure is something like this. So this zone is for weak shock. So for weak shock, this figure is for chemically reacting gas, and this is for calorically perfect gas. So for chemical reacting gas, for weak shock, the beta angle which we are getting, shock angle which we are getting for oblique shock is less than which we get for chemically perfect gas. For for chemical reacting gas, the beta is less than beta for chemical reacting gas, and generally weak shock only occur in the nature. So for this statement 2, it is talking about only weak shock only. The oblique shock for equilibrium high temperature chemically reacting air lies further away from the body compared to chemically perfect gas assumption. So we have seen that it is not further away, it is nearer to the body. So this statement is false. And statement first was true because theta max for equilibrium high temperature chemically reacting air is increased compared to chemically perfect gas assumption. So statement 1 is true and 2 is false. Option B is correct. And one more thing, if you see for the strong shock, the beta angle for the strong shock is greater than beta angle for strong shock for chemically reacting gas is greater than beta for chemically perfect gas. This is one thing which is different from the weak shock. You can see like this also in the last table. This table we have seen that rho 2 by rho 1 for chemically reacting gas is greater than for chemically perfect gas. This is for normal shock, but for the oblique shock also this rho 2 by rho 1 will be greater than from chemically reacting gas, chemically perfect gas. So as rho 2 is high for same rho 2, for same rho 1, rho 2 for this chemically reacting gas is higher than rho 2 for calorically perfect gas. So for same mass flow to pass through the shock, the shock layer should decrease because rho 2 is high. So if shock layer decreases, then the same mass flow will pass through the shock. So that's why the shock layer will decrease further. Now we'll see the next problem. When oxygen is T0 equal to 5000 Kelvin, P equal to 1 atmosphere is expanded through a high area ratio nozzle. It is found that option A, O atoms recombine to form O2. Option B, recombination is an exothermic reaction. Option C, recombination is endothermic reaction. Option D, 0 point energy of 2 O atoms is greater than 0 point energy of 1 O2 molecule. From this you can see only one of these can be true. Okay. We already know that across the expansion, whenever there is expansion, the temperature decreases. So due to decrease in temperature, the recombination reaction happens and O atoms will combine and form O2. So this A is true. And the recombination reaction we also know that it is exothermic reaction, which is so B also true and C will be wrong. and we have already seen that the 0 point energy of two atoms combined will be greater than 0 point energy of a molecule. If there is, let's say, dissociation or decombination of two molecules, so this delta will be greater than 0. For this option D is also correct. So what happens that due to the expansion, the recombination of atoms happens, and as recombination is exothermic reaction, this sum of energy of this reaction will go to translational and rotational modes also, due to which the energy in translational mode for this chemical reacting gas will be greater than energy in the translational mode compared in chemical effect gas. So let's say this is energy in the translational mode will be greater than energy translational mode for chemically reacting gas will be greater than energy for in the translation mode for the calorically perfect gas. So due to which temperature for the chemically reacting gas will be greater than temperature which we found in calorically perfect gas. So the flow will be slightly hotter in chemically reacting gas compared to calorically perfect gas. Now we'll see what is equilibrium flow and frozen flow. After it we will see one more problem related to it. So what happens in equilibrium flow? In equilibrium flow, there is no change in chemical composition and there is no change in any flow properties also. So if there is no change in chemical composition, it means that it has infinite chemical and vibrational rates, because there should be local thermodynamic equilibrium also. Let's say there is one flow is happening, so at different points of flow there will be different wave properties also. But if there is equilibrium, then let's say one particle is going from one point to another point. So if there is equilibrium flow, then this change in properties should be instantaneous. It should not take any time, so there is infinite chemical and vibrational reaction rate. Therefore, equilibrium properties of a moving fluid instantaneously adjust to local temperature and pressure as it moves through the field. So it adjusts instantaneously from one pressure and temperature to another due to infinite chemical and vibrational rate. Frozen flow is its opposite. It has zero chemical reaction rate and vibration rate. So what happens is its chemical composition of the flow and chemical composition of the flow remains constant throughout. This is for invisible flow. For the viscous flow, due to dispersion, due to diffusion also, there can be change in chemical composition of the mixture. But here we are talking about only viscous flow. Now one thing is to see that Equilibrium flow there is infinite chemical and vibration rate, and in frozen flow there is zero chemical reaction rate. Both things are not possible. Either chemical reaction are not happening, or if chemical reaction is happening, zero chemical reaction rate means chemical reaction not happening at all. So if there is chemical reaction is happening, then it is not possible to have zero chemical reaction rate. So we define generally this equilibrium flow and frozen flow by reaction time and flow time. Reaction time and flow time. Let's say this is TR and this is TF. So if it reacts, then this is chemical reaction time. So if time taken for chemical reaction is very short, compared to flow time, if TR is less than TF, or you can say very less than also. If reaction time is very less than flow time, then flow is equilibrium flow, because reaction will already have happened before the flow was completed. And if reaction time is very greater than flow time, then flow is called frozen. Flow is taken as frozen because reaction is not happened fully, but while our flow has completed. So why does it take time for reaction to happen? Because generally reaction also happens due to the collision of particles. Only when collision happens, there is possibility of chemical reaction. So due to the mean path distance, mean flow path, and this collision frequency, some time takes for collision to happen, but that time is only responsible for the chemical reaction time, due to which it is not possible to have infinite chemical reaction rate. For infinite chemical reaction rate to happen, the collision frequency should be very high, but it depends on pressure and temperature. Collision frequency depends on pressure and temperature, so it cannot be infinite. Now we'll see one more problem. So that speed of sound in equilibrium chemically reacting gas mixture is given by AE square equal to gamma RT 1 plus 1 by P dou E by dou V at constant temperature upon 1 minus rho dou H by dou P at constant temperature. So first we should know what is the speed of sound. The speed of sound is given by A equal to under root dou P upon dou rho at constant entropy. This S is for entropy. Constant entropy means for isentropic flow. So flow across a sound wave is isentropic. Now we'll see the derivation. For equilibrium flow from first and second law of thermodynamics, TdS equal to du plus PdV. In the first law we have substituted dt equal to TdS. Similarly, TdS equal to dH minus vdP. Now the process through sound wave is isentropic, which we already told before, so TS will be 0. As TS is 0, we will get equation dE plus EdV equal to 0 and dH minus EdP equal to 0. Now we already know that for equilibrium chemically reacting gas, the mixture, reacting gas mixture, E is function of V and T. So we can write total differential dE equal to dou E by dou V at constant temperature dV plus dou E by dou T at constant volume dt. And we know that dou E by dou T at constant volume is nothing but Cv. We'll substitute the Cv. So we'll get dE equal to dou E by dou V at constant temperature dV plus Cv dt. Let's name this equation 1 and 2. So if you substitute this equation third in equation 1, we will get dou E upon dou V constant temperature dV plus Cv dt plus EdV equal to 0. Or this is from 1 and 3rd. This dV term we can take together, so it becomes Cv dt plus E plus dou E by dou V at constant temperature dV equal to 0. That's my equation 4. Similarly, H is function of pressure and temperature. So we can write its total differential also, which will be dH equal to dou H by dou P at constant temperature dP plus dou H by dou T at constant pressure dt. And we know that Cp equal to dou H by dou T at constant pressure. So we will get dH equal to dou H by dou P constant temperature dP plus Cp dt. This is equation 5. Now from this equation 5, if we substitute this dH into equation number 2, this one, from 2nd and 5th, we will get dou H upon dou P at constant temperature dP plus Cp dt minus V dP equal to 0. We can take the dP term common also. We will get Cp dt plus dou H by dou P at constant temperature minus V dP equal to 0. This is equation 6. If we take this term on the right hand side, so here are only I will write it, so this term will become negative. Similarly, If we take this also on right hand side, this term, then this also will come negative. If we take the ratio of 6th and 4th, 6th and 4th, then we will get Cp by Cv equal to in this one also there is minus, in this one also there is minus, so there is no need for writing it. It will become dou H upon dou P at constant temperature minus V upon P plus dou E upon dou V at constant temperature into dP upon dV. Now we know that V equal to 1 by rho so we will get dV equal to minus 1 by rho square d rho. So our this equation will become, we will substitute it, Cp by Cv equal to dou H by dou Pt minus V upon P this V also I will write 1 by rho E plus dou E by dou V T, and this derivative will become minus rho square dP upon d rho. We will take P outside from here and multiply rho here. So we will get 1 by P rho dou H upon dou P T rho dou H upon dou P T minus 1 upon 1 plus 1 by P dou E upon dou V T minus rho square, and we have taken isentropic flow across sound waves, isentropic flow. So this dP by d rho will be nothing but dP by d rho isentropic S. This we can substitute as A square, which is nothing but the speed of sound in equilibrium flow. So you substitute it, and this 1 rho will cancel 1 rho, and this minus 1 will multiply it inside. So Cp by Cv equal to this rho by P 1 minus rho dou H upon dou Pt upon 1 plus 1 by P dou E upon dou V T and dou P by dou rho as A square. So this P by rho also we can write it as P by rho equal to RT and Cp by Cv equal to gamma. If we write these two things, then we will get A square equal to Cp by Cv equal to gamma. This P by rho will go that side, so gamma RT 1 plus 1 by P dou E upon dou Vt upon 1 minus rho dou H upon dou Pt. This is the relation that we have to derive. So we got this relation. This is nothing but speed of sound in equilibrium flow. And now we will see for frozen flow. So in frozen flow, there is no chemical reaction. So gas will behave as thermally perfect gas or calorically perfect gas. In both cases, E is function of for thermally perfect gas, E is function of temperature and H is also function of temperature. This is for thermally perfect gas. If we see for the calorically perfect gas, this derivative dou E upon this E will be function of in both cases this E and H will be function of temperature only. So what will happen that dou E upon dou V T will be 0 because temperature is constant, so its derivative will be 0, and dou H upon dou P T will also be 0. at constant temperature, the value of H and E will not change. So if we put this derivative, let's name this equation is equation A. Let's put this derivative in equation A. From equation A, if we put this derivative as 0, put this derivative here, this term will go 0, this term will go 0, and this fraction will come as 1. So this AE also will write as AF. So we'll get EF square equal to gamma RT, or simply AF equal to under root gamma RT. This is speed of sound for frozen flow. Frozen flow, or you can say for chemically perfect gas or thermally perfect gas also. Similarly, this speed of sound is for chemically reacting gas also. Now let's see a plot of speed of sound versus temperature. Speed of sound AV square P by rho by P. So for frozen flow, it will equal to 1.4 for air, but for the equilibrium flow, it will depend on different pressures. These different value of pressure, these plots are given, and the value will vary. You can see that this value, if let's say at this point, this value is 1.4, and for this curve it is 1.3. So this is very big difference. So that's why there is very big difference in speed of sound for equilibrium flow and frozen flow. That's why we have used only velocity till now. We are not using the Mach number, because it is very difficult to define a Mach number, which speed of sound to use. So if we use the frozen Mach number, let's say if we use the frozen Mach number, then MF equal to U upon EF, and if we use the equilibrium Mach number, then E equal to U upon A. So as this EF and AE are very big difference, so this MF and ME will also be very big difference. That's why we are not using Mach number in this for this high speed flows. It is not very useful. One more, this speed of sound has this derivative dou E upon dou V at constant temperature and dou H upon dou P at constant temperature. We have curve fit which give value of E as function of E Vt and H as function of E Pt. So using this curve fit or polynomial correlations, we can find its derivative and plug in directly in this equation and find what will be the speed of sound. And that curve fit is given by tan L. And okay. So we have derived for speed of sound for both chemically reacting gas, for equilibrium flow and frozen flow. Today we will see one more thing, that we have seen what are the equations for coordinate equation for normal shock, for chemically reacting gas. But we have not solved it. So we have seen that before in the first problem itself we had write three equations: Ut equal to rho 1 by rho 2 u1, first equation, P2 equal to P1 plus rho 1 u1 square 1 minus rho 1 upon rho 2, and H2 equal to H1 plus u1 square upon 2 1 minus rho 1 upon rho 2 whole square. And one thing to notice that this H is not function of temperature, it is function of temperature and pressure, two thermodynamic properties. So it is difficult to solve it analytically, we have to solve it numerically only. So solving the numerical, there are some steps. First one is that we have to assume value of rho 1 by rho 2. Let's assume we have assumed some value, let's say 0.1. See, now we know that rho 1 by rho 2. So using this rho 1 by rho 2, we will calculate P2 and H2. P2 and H2. P2 and H2 we will calculate here. And there is one, this rho 2 also can be, all thermodynamic properties can be given as function of two other thermodynamic properties. So rho 2 is also function of P2 and H2. So using calculate, so using this P2 and H2 we will find this rho 2. Now we got this new rho 2, so we will get new rho 1 by rho 2. Using this new rho 2 by rho 1, we will repeat step 1 to 4. So we will repeat it till we get the convergence. It means rho 2 till, we will do it till rho 1 by rho 2 rho 1 by rho 2 mu minus rho 1 by rho 2 old, its mod is less than epsilon, where epsilon is 10 to the power minus 3, or you can take better convergence also like 10 to the power minus 6 or something. Like this we have to solve the normal shock. Similarly for oblique shock also we will get one more equations which will have the theta and u relation. Using that we can find angle also. Using that 4 equation we will find similar kind of iteration we will do and find the solution. And one more thing we have used is this functional relationship of rho, and it's dependent on preference and enthalpy. This can be found in Daniel curve fit, which is given in this chapter 11 of this hypersonic and high temperature electronics also. In this many curve fits are given. Curve fit, and these are the polynomial correlation of the calculated and tabulated data. So there are some relation like pressure as function of E and rho, temperature as function of E and rho, H as a function of P and rho, okay, in this one only these are given. So you can actual curve fit, there is also, I think, this curve fit is also given, or density is function of H and P. Otherwise you can do it different way also. Like you can use this preference density relation. You can assume this H2. Let's say we have assumed this H2, and using this relation we found the value of rho2. This known rho2, you will find the value of u2, and you will find the value of this p2. So we will got the value of rho2 and p2 using this rho2 p2 and this relation h e rho. You can find a new h, and you will repeat the iteration like this. So in Daniel curve fit, what is there, that this polynomial relation is given. So like this relation is given, and it is a function of many coefficients also, which will depends on the range of preference density. So in these tables also, this value of coefficient is given, and you can take it and put it in the equation and find the value of enthalpy. Like this, you have to use the curve fit to find the properties of process shock. You can search this curve fit by the name Daniel curve fit. You will find it. So today I will stop here. Okay, thank you.